So today we would like to thank you, Dr. Xing Fang, that comes from United States, and he's presenting for us two main activities that are first a seminar, a course on water quality on surface waters, and then this small seminar about projections of climate impacts on water quality characteristics and fish habitats in lakes of the contiguous United States. This is part of the CAP Sprint program. The CAP Sprint program aims to internationalize universities around Brazil. We are very happy that we count with the presence of Dr. Xing, and also Dr. Xing is here to establish links. So any of you that likes this presentation or are enrolled in the course and may like to spend some time in the US, maybe for a full position as Ph.D. candidate or master candidate, you can contact Dr. Xing. Also, he's open to partnerships in research. I will not tell the full CV of Dr. Xing, but he has published something like 180 papers in journals, and he has advised many and many people. So I will just let him talk, and I thank you all for coming here and take your time in this end of semester. I know it's not easy. We are totally full of activities. It's not the best time for us, but you are resilient. And you and me, we will learn a lot in this moment. Thank you, Dr. Xing.
Okay, thank you for everyone. Thank you for the introduction for Professor Daniel, and I'm so happy for this opportunity to visit your university. This is the first time for me to visit Brazil, visit the university, and I had a great experience so far, and thank you. Okay, so my seminar is something kind of different, and I'm doing some research also dealing with hydraulics and hydrologic study, but also I'm doing some other research dealing with water quality. And also you look at the keywords, fish habitat. That's not like a traditional study for civil engineer or environmental engineer. And I want to explore this idea and how we get this like interdisciplinary study, and also you see in lakes over the contiguous USA. So there's over large area. How do you do those type of studies? And maybe you'll find some interesting point how we approach and solve this challenging problem in this way. And if you look at the climate change impact, that's the big picture. So we want to find out how the future climate warming will impact the lakes and then go have impact the fish habitat. So that's the big picture. As Dr. Daniel mentioned that, so if you want to contact me, you have questions about my seminar or some other question, so this is my email address. It's pretty easy, just my first name, my last name at auburn.edu, and that's my homepage. You can find out more information. And my study actually presentation will go through different area for 3 study. And the first is methodology to estimate global climate change impacts on the lake and stream environment condition and fishery resource in Minnesota. So that is the first US EPA, Environmental Protection Agency, funded for a study for a couple of years. And so that is, Minnesota is just like one state. And after that study, we applied like the second funding. So we applying the study for whole contiguous USA. So the only thing we exclude is like Hawaii, Alaska, but include.
Sorry, people's complaining
Okay. So the second one is start alternations of water availability, water quality, and fish habitat in small lakes in contiguous USA. So we moved from one state to whole contiguous USA. The third phase, we go back to the Minnesota again. And in both the first and second phase, we start the fish habitat. And you know there's many different fishes. We're not able to study maybe individual one. So we group the fish into three called the categories. We call the cold water fish, cool water fish, and warm water fish, okay? But the third phase, we back to a specific fish called a cisco, and it's a cold water fish. And we try to identify the refugee lake, which I'll define, okay? So let's just give you a big picture. So we're dealing with future climate change. So my research is not try to find out future climate condition because we are not doing the climate study. We just use their results, okay? So we use like the GISS, GCM, and the Golden Institute Space Study Global Circulation Model. We use the Oregon State GCM model, United Kingdom GCM model, and the Canadian Climate Center and CGCM model. So these are the climate projection from these global circulation model. So we just use their projection to do our study. So let's give you a big picture. We use their climate projection. This is our lake model, and it's one-dimensional. So basically, we start a temperature change from water surface to the lake bottom. We only include the change along the vertical depths. And for the lake, there's many things going on. You have inflow, bring the water, nutrients, send them into the lake. And you could have a density current for settling entrainment. And in here, on the surface, you could have wind blows on the surface. You mix the lake. And on the surface, you definitely have a surface heat exchange, and so on. So this model was originally developed in 1980s. And the first version and mini Lake 87. So this basically is a Minnesota lake model, 1987, okay? And I went to Minnesota in 1990, okay, and started using this program and did lots of expansion. So we got a version 96, and at the end of my postdoc, then I moved to another university, so we still continue expanding the model. So current version we call the Mini Lake 2020 in that way, okay? This is a basic schematic, just give you some idea in the lakes. There's many things going on, and such as dissolved oxygen is linked to the surface aeration, and also linked to the photosynthesis of the algae. And algae, you have respiration, you have the zooplankton eat the algae, and algae will need the nutrients, and so on. So this is a very complex model in the early version. But in the 1990s, we got the project from US EPA. So we want to project the water quality condition in lakes. First, we did in Minnesota, okay? And I don't know whether you know how many lakes in Minnesota, okay? They call the 10,000 lake state. So there's many lakes. You want to project their condition in the future. Sure, you cannot simulate these 10,000 lakes one by one, right? So that's the first challenge. How do we tackle this issue? Okay, and also because of talk about the future, there's many information unknown. So we need to simplify model, instead include all the mechanism, and essentially we only simulate the two parameters. One is water temperature, another one is dissolved oxygen, okay? Because eventually we want to start a fish habitat, okay? Fish, and there's two important parameters control their existence. The first one is oxygen. Just like us, we breathe, okay? If there's not enough oxygen, fish cannot survive. Okay? The second one is temperature. I mentioned we classified the fish to cold water fish, cool water fish, and warm water fish. These different fish category have different temperature requirement, okay? Such as for cold water fish, if you go to the area too warm, they just cannot survive there, okay? So that's why we simulate these two key parameters which have a direct input and to the fish habitat, okay? So we did lots of advancement. So first of all is 1D, we have different vertical layers, and originally we only simulate the open water season. Later, so we simulate ice cover period, especially when we did a study in Minnesota. In Minnesota, from October to March or April next year, the lake is covered by the ice. So our model need to simulate the ice and the snow. So we advanced the model for both open water and the ice cover period. And then for dissolved oxygen, so we include like the oxygen production by photosynthesis, respiration, biochemical oxygen demand, sediment oxygen demand, and so on. And just like this morning for our lecture, we mentioned in the summer for deep lakes, this is a typical temperature profile, okay? And over there, this is the winter profile. And at the ice water interface, 0 increase to 2 degrees, and more or less constant increase to 4, okay? And in order to more accurately simulate the water temperature, we also need to simulate the temperature in the sediment. We simulate the 10-meter sediment layer temperature changes. So in here, you have the sediment temperature changes over there. In the early time, we only simulate the sediment layer in the deepest part. And later we expand the model, we simulate the heat exchange between the water and sediment for each layer, okay? Then we have the 2 papers in the water resource research about this topic, okay? And this is the typical DO profile. So just give you a quick idea. So this basically is a governing equation to simulate the water temperature, TW, as a function of time T. And our time step is 1 day. So we simulate the temperature profile every day. And we simulate like in the summer and through the winter, and then go through year by year. The early time we study is from 1961 to 1979, because at certain time they say in 1980 they already have some climate warming indication, so we stop in 1979 in that way. But right now the model, as long as you have climate data, we can simulate like from 1961 to 2023 continuously, day by day. And then click a button within a few minutes, you get a temperature DO profile each day in that way, okay? And this is just to show you a little bit more. We divide the lake into layer 1, layer 2, layer 3. On the surface, you have these different heat component and atmosphere radiation coming in, and you have an incoming solar radiation that is short wave. Part of short wave is reflected, and part will be penetrated down to the water, heat the remaining part of water. And you have evaporation, convection, and back radiation. So this is a little bit about the model. And this is a dissolved oxygen model. Dissolved oxygen and in the water is connected to so many different things. And the one thing is about oxygen production by the photosynthesis for those aquatic plants we call the algae, okay? So right now we are encounter one issue. We mentioned that. So Minnesota, you have 10,000 lakes, okay? But we don't want to simulate 10,000 lakes. Then you ask how many we should simulate? Few hundreds or just few, okay? Eventually, and my advisor and developed this brilliant idea. We simulate 27 types lakes. Not 27 lakes, 27 types lakes, okay? So we classify the lakes based on the surface area, maximum depth, and then called the trophic status, okay? So in here you see for the lakes or for any water body, And we classify as oligotrophic, mesotrophic, eutrophic lake. So basically, for those lakes, it's very productive. Typically, it's more turbid. There's more maybe aquatic plants and growing. There's towards more eutrophic lake. For those lakes, it's very clear, and you don't have much algae growing, and it's oligotrophic lakes. Okay, how can we know the lake is in eutrophic, mesotrophic, oligotrophic? For our normal citizen, a simple way is we look at transparency, how clear. How do we measure the clear of water? We use a so-called Secchi disk depth. And some of you, if you had limnology or biology class, you may know, is this metal disc painted as black, white, black, white. You load it into water up to point you don't see. That is giving you a depth, okay? If the water is very clear, you load down to many meters, you can still see the disc because it's black, white, and most contract. But for some lake, it's turbid. You just load down 1 meter, you're not able to see that disc. It's become eutrophic, okay? So basically, we use this Secchi disk depth. And for the eutrophic lake, they have more algae. The algae have a more chlorophyll A. You know those green pigeon in the plants, okay? So eventually, for trophic status, and based on, these are recommended like a border, so we pick up some representative data points for these different classes, which we'll show you in here, okay? So in this diagram, the x-axis is chlorophyll A concentration. There's a direct connection to the trophic status. And this is a surrogate measurement, Secchi disk depth, okay? And you look at data, so they have a pretty stronger correlation. So when the Secchi disk is larger, go up there, okay? Chlorophyll A is lower because it's more clear. When the Secchi disk is smaller and the chlorophyll A is larger, it's going to decrease. And those box is giving you some boundary for oligotrophic, mesotrophic, eutrophic lake. You see 3 large dark dots. Those are the 3 representative value we selected, okay? So 1 is for oligotrophic lake, and I think the chlorophyll A is 2 microgram per liter, and then we have 1 for mesotrophic, 1 for eutrophic, okay? And also we know the algae is growing in the spring, there's a change in the summer, maybe there's a fall bloom again. So we, based on some study by Marshall and Peter in 1989, so we did post a pattern, okay? So we assume annual average, and then we use this pattern, make them change day by day also. And actually we have 2 patterns. One pattern is for eutrophic lake, mesotrophic lake, and this is for oligotrophic lake, okay? So we do have a chlorophyll concentration as input every day. And this is show you one of the simulation results in Thrush Lake and at 5 different depths. 1 meter, 4, 7, 11, 13 meter below the water surface. Open circles are our data points, and the lines are simulated by the model. So that's just show you we have a model, we made some simplification, then we take some actual lakes to do the modeling and see whether the model matched the observation relatively well. And also this simulation is for multiple years. This is from 1989 to 1991, so cross about 6 years. So you can see go into the summer, winter, summer, winter, summer, and we can do the simulation year-round, continuously, from summer, winter, and so on. So that's our model performance, okay? And this is I show another results for another lake, and just for 2 years. And in here we show you the temperature, okay, and then DO. Surface about 1 meter below and 40 meter below. Also, you have simulated and measured, okay? So give you similar information. Okay, this is our 27 lake types, okay? I just mentioned like eutrophic lake, mesotrophic lake, oligotrophic lake. And we use the second disk depths, 1.2, 2.5, and 4.5 meter. So clear oligotrophic lake, you put the disk down up to 4.5 meter, you can still see the disk. But for eutrophic lake, you just put the disk down 1.2 meter, you're not able to see anymore. Okay, so that second disk depths show you eutrophic, mesotrophic, oligotrophic lake. Okay, other two parameters we used is the maximum depths. Okay, we select the 4 meter represent the shallow lakes, 30 meter represent like a medium depth lake, and 24 stand for deep lakes. And you may ask why we pick up those values. So first of all, we had more than 1,000 lakes database. So we did some data analysis and then pick up certain certain percent, and we assume it's a shallow lake and so on, okay? The next one is a surface area. So we have a small surface area and a medium surface area, large surface area. For small surface area is 0.2 kilometer square, okay? For medium surface area is 1.7, for large is 10 kilometer square. Okay, so we have three maximum depth category, 3 area category, 3 second disk depths, 3 by 3 by 3, we got a 27 combination. So lake type 1 stand for what? Shallow, small, eutrophic lake. And lake 17 stand for medium, large, mesotrophic lake. Okay, so we get a 27 combination of lake types. Okay, so even though Minnesota you have 10,000 lakes, and you pick up a lake, maybe you can find out your lake is related to one of the lake or between these two. Okay, we also, based on study, find out important parameter called the geometry ratio. It's a surface area in square meter to the component 0.25 divided by maximum depth. Okay, so basically, if you look at that number in here, okay, if you want to make this whole number to be smaller, you have to make your surface area smaller, maximum depth to be larger. Okay, when this number is smaller, it means stratified. You have a deep, small, and wind have a hard time to mix. Okay, if this number is larger, so you have to make a surface area larger, maximum depth shallow, and wind blows over can mix the water, make them more or less well mixed. Okay, so these are the value of the lake geometry ratio for these like 27 lake types, because this geometry ratio is not linked to the second depths, only 2 parameters. So that's why these 3 lake types have the same value. Okay, so you can see the lowest value is 0.9, the highest value is 14.1. Okay, basically when this number is about less than 3, we say is strong stratified. Between 3 to 5 is kind of weak stratified in transition. If it's 5 or more, close to 10, is more well mixed. The lake can mix many times a year. So basically, like looking around, you may see some lakes, ponds in your area. You look at 2 numbers. Ask the surface area, maximum depth, and you can do this simple calculation. You get this idea. This lake in the summer could be mixed several times or could be strong stratified. Okay. So then we did a study from Minnesota. So that is Minnesota. Okay. Then we came to the contiguous USA. So essentially, we select 209 cities. So those are like dots, okay? And the cross are the basically grid center where the global circulation model has a future projection, okay? So such as for this station, this will use the projection in here to show the future climate in that way, okay? And so we have 209 stations. At each station, we have 27 lake types. In the reality, they may not have, okay? But each location will soon have 27 lake types, okay? So we do the lake modeling for 209 stations, and then for each station, we run the model for 27 lake types to do the projection, okay? So this is to give you some results and relate to the information. Why is impact on snow and ice cover characteristic? This is the maximum ice thickness on lake. And essentially, we talk about the difference, GCM minus PASCE. So you see the difference is minus 0.3, 0.2, 0.1. So they mean that due to the future climate warming and snow thickness will be reduced, okay? And the maximum they may reduce up to about 0.3 meters in that way, okay? So there's some other parameters we also study, and this is ice out date. So you have the ice formation in the winter, and then in the next spring, ice melt down. Okay, so this is show you similar the ice out date. Okay, those are the number. You see 110 is stand for April 20th. That's what we call the user junior day. And January 1st is junior day 1, and so on. Okay, so you can see in northern part of the United States, like in the past climate condition, and the ice out can be as late as April 20s. But on the future climate condition, so you see this become like a 90, okay? And it become March 31st. So the difference is about 20 days. Can be shortened about 3 weeks in that way. And this is show you annual cumulative day of ice cover on small, medium depth lake. Let's talk about how long ice will cover. Okay, on the past, you see it's 150 days, so about 5 months. Okay, the lake is covered by the ice in the northern United States. Sure, in the southern part. Okay, so basically, if I give you some picture in here, okay, so this is Alabama, and Auburn is somewhere in here. Based on this diagram, you see the lakes over there. There's no ice cover like in here too. Okay, but I study Minnesota. That's on the top over there. Okay, so this is basically Minnesota, and then you have the ice cover. Okay, the lakes over there is covered by 5 months in that way. Okay, so that's the past, that's future. So basically, you can see the ice cover changed from 150 days. Okay, actually this gives you the difference. Future minus past, you see difference is 45 or 60 days. Okay, due to the climate change, the ice cover period is reduced up to 2 months. Okay, and for some winter lakes, and which actually have the positive impact, which I later will show you. I don't know whether you heard so-called winter kill for fish. Okay, so in northern states, in those shallow lakes, and in the spring, when the ice melts down, some of the small lakes, when they melt down, whole lake is a dead fish. That's called winter kill. Okay, because basically it is for those small lakes, and when the winter cover is too long, and all the oxygen has been consumed, at the end, whole lake, there's no oxygen, so all the fish is completely killed, called winter kill. Okay, because this ice cover period is reduced, and winter kill will be removed for future climate, which is a positive impact for the fish habitat, which I'll show you later. Okay. This is on the temperature characteristic. Why we show you the annual evaporation water loss, okay, and the future minus past, as positive 0.3, it means that in the future you have more evaporation, lose the water. Okay? And this is the maximum lake surface temperature, and you can see there's a strong dependence on geographic situation. Okay, let me see. It doesn't show the past, but this is the maximum. Okay. So you can see on the north, the maximum about 24. By the way, go to south, can be up to 30, 32 degrees Celsius. Okay, this is the difference. Okay, so due to the future climate warming, they can increase to 3 or 4 degrees. Okay, this is another diagram we use in our paper for so many studies. I mentioned that we only simulated 27 type of lakes, and we developed this diagram. And the y-axis is the second disk depth, which is indicate trophic status. And the x-axis is the lake geology ratio, is indicated how strong of stratification. So in here, we have 27 data points for those 27 lakes. Okay, so for any Minnesota lake, if you get these 3 parameters, you'll find out data point in here. Okay, we do the simulation, so we have results on these 27 points. Then we can create a control line. If the control line is consistent, then you have another lake is falling here. We can interpret the results and to find it in that way. Okay, even though we did the lake, the maximum area is 10 kilometers square. We even find some other paper, they did a study for Great Lakes, which is much, much larger. Then we use these 3 parameters and we find out data point is in here. Then we look at our results and their results is very close. Okay, so we can even extrapolate beyond our database region. Okay, so this is a results with using the simulation. So this is the simulated surface, simulated maximum temperature difference between lake surface and bottom. So basically you have lake. We pick up the temperature 1 meter below surface. We pick up the temperature 1 meter above the bottom. We look at the difference of those temperature. Okay, if the lake is more or less well mixed, those difference is about 0. If it's a strong stratified, there are large difference. Okay, so you see, basically we have 27 data points. Then we use the software and to create a control. So you see they have a clear pattern. If they don't have clear pattern, all these will be scrambled. Okay, and it means that when we present the results in this way, we can get a better series pattern. Okay, so you see the difference in this region is more than 16 degrees. Okay, and then you see point A1, 3, let's say 3 is here. Okay, so for stratified the lakes, like in Duluth, Minnesota, their temperature difference can be 10 up to 16 degree difference. Okay, but when you look at the geometry ratio, that's about 10. Okay, you see their difference is only just about 1 degree or less. Okay, so it means that we use this 27 lake type classification, just simulate 27 lakes, we can get the results, get information for many, many lakes. So even though in Minnesota we have 10,000 lakes, we only simulate 27 lake types in that way. Okay, so I think that was a very brilliant idea my advisor invented, and we used in so many studies in that way. Okay, so so you see these are for 4 different areas. So even though you see the magnitude is different, this is Austin, Texas. Okay, this is Charleston West, but if you look at the pattern, it's basically similar trend. Okay, you can see clearly stratified lakes, more or less mixed lakes. Okay, and then we back to the dissolved upstream. Look at the lakes in whole contiguous USA. Okay, we look at the minimum surface dissolved upstream during the open water season. So you see in north part, and they may be up to 6 milligram per liter, okay? And both are dealing with the future, okay? This is 7.5, okay? Lake 7, Lake 9 has the same maximum depth, same surface area, but the Lake 7 is eutrophic lake. This is orogenic lake. So that's why the DO is higher in here, 7.5, okay? Which I'll show you, but you may guess, such as for fish, what is the minimum DO that may need to survive for DO? Do you have any idea? 2 milligram, 3 milligram, 4 milligram? Okay. It's about 3 somewhere, okay, conservatively, okay. So you see, this is in the surface, okay, there's a 6 and 7.5, that's fine. But you consider deep, and then the bottom, there's no oxygen, okay. Another thing is maybe you went to the lake or reservoir before, a huge lake reservoir. During the summer, only surface there, there's enough oxygen. Below that is a huge amount of volume of the reservoir. Actually, there's not enough oxygen. Fish cannot stay there. Okay, you may not realize, but that's the situation. Okay. And okay, this is now we mentioned the winter kill. Okay, so we are plotting the dissolved oxygen, semi-dissolved oxygen in the whole year, January to December. Okay, this is a shallow lake from 1 to 4 meters. Okay, so on top, and the following the dark line showing the ice cover. Okay, so this is for the past. This is for the future. We call it 2 times CO2. And first, we can see the ice cover period. Past is longer, and the future is shorter. Then you look at DO. In the past, you see for this area, okay, from maybe middle of January to middle of April, okay, and whole depth, oxygen is 0, okay. That is called the winter kill. And if you have the fish, the first ice cover, they cannot go anywhere, and they just stay there. And the oxygen is continue to decrease up to the point no oxygen at all. All the fish are killed. So at the April, when the ice melts out, whole lake is a dead fish. That's called winter kill. Okay. So if you go to northern states, in US or any part, this can happen. And actually, it's just add an insert. So when I was a student, I also received a newspaper from China. And when I do this study, I just look interesting. We also sometimes do the agriculture. They use a pond to raise fish. What they show to do is that those workers to wipe down the snow. Why they want to wipe down the snow? Because basically a very thin layer of snow can attenuate all the solar radiation. But ice is clear. Okay? If you wipe down the snow, let light through the ice get into the water, and then they can make the algae produce oxygen continuously, even though it's ice covered. Okay, they can produce oxygen even on the ice cover. So what they do is try to wipe out the snow in that way. But for these natural lakes, it's huge. Nobody can just like wipe out the snow in that way. But for the small fish pond and for the winter, you can do that. Okay, but the idea is to make them produce the oxygen. And okay, but you see for the future, and the DO can still maintain 1, 2, 3, and 4 milligram per liter. So the fish can still stay there in the future. That's what we're talking about. Okay. Okay, this is our schematic diagram, because what I discussed so far, I talked about the temperature and dissolved oxygen. How do we connect to the fish habitat? Okay, so we define like a so-called LT, the lethal temperature for fish. If temperature is about that, the fish will not be able to survive. And then they have a UGGT, LGGT. This is up or low good growth temperature. So when the water temperature is within this range, the fish has the best condition for growth. And then this is for the DO. When the DO is less than 3 milligram per liter, and it's kind of lethal.
Okay, but for the warmer water fish, the criteria is 2.5. This diagram is to show you could have a summer kill. Okay, because basically if you have fish, if you go up, it's too warm for stay here. If they go low, DO is too low, they cannot survive. Go any other depth, there's no existence. So this is indicating you have so-called summer kill. Okay, if these two lines is do not intersect, which I show you, then the fish can stay in the middle, and, okay, in that way. And so the white area is basically temperature is less than lethal temperature, but it's about good growth temperature or lower than the lower good growth temperature. They can survive, but it's not a good condition. It's called restricted growth. So in this case, we can indicate which part you have the uninhabitable condition, which part you have good growth, and which part you have restricted growth. We use the two parameters. Water temperature we simulate every day, and dissolved oxygen we simulate every day. And we can do the study for a whole year in that way. Okay? And this is just some number. So that's what I'm talking about. We classify the fish to cold water fish, cool water fish, normal water fish. Okay? And I only list one for you, such as for cold water fish. And these are some of the fish species, like a brook trout, brown trout, cholo salmon, and trollman salmon, coconut salmon, mountain whitefish, pink salmon, and rainbow trout. Okay, so you may be familiar with these fish, but they group together as so-called cold water fish. And we will also have a list, but I'm not giving you here for cool water fish, warm water fish. These are the criteria determined by the fish biologists. So during the project, we had the fish biologists as a part of the team. They provide this data for you, okay? And but my part is doing the temperature DO modeling and couple them together to the projection in that way. And also dissolved oxygen, we contact the experts in the US EPA. So they give us those criteria, DO 3 milligram per liter, or warmer water fish is 2.5 in that way, okay? Okay, so this is basically indicate summer kill in one of our study lake. And that summer is warmer, and they go there, they find out fish is floating on the surface. That's summer kill. And this is a simulated result, okay? So this is past for 2008 climate, that's for the future, okay? So this is from the whole year. So you see here, this part is too warm, this part DO is too low, but between them you have a gap. So fish can survive in this past climate condition. And this is for whole depth is a good condition for them to survive. And then if you look at the future, so you see, and this warmer temperature and the low DO start intersect. So that's you got so-called summer kill, okay? And it goes up too warm, go down, DO is too low. And because when you draw a vertical line, this is indicated at a particular date. Okay, so this is an indicator you have summer kill. Okay, so there's some other example. So these are indicated what? Winter kill. Okay, because in the whole depth, okay, the DO is less than 3 or 2.5 milligram per liter. Fish cannot stay there. Okay, that's for the past. Now, if you look at the future, they still have some space for them to stay there. That way, okay. But for this lake, they got a summer kill. They changed the winter kill to summer kill because it's summer and everywhere is too warm. Okay, so we find all these different situations and switch back forth. Okay, so these are shallow, just 4 meters. So this is deep, 13 meters. So you see in here, there's a gap. But for the future, they intersect again. So they get a fish kill in here. Okay, but in here, the surface never get too warm. You have plenty of space for fish to stay in here. For the winter, you have plenty of space also. Okay. So eventually, and we get this summary graph. So we have more than 200 cities, and in each city, maximum we have 27 lake types. Okay, this is for cold water fish. So for those like a red one, it means that in that pond, and all 27 lakes can support a cold water fish. If it's 27. Okay, then if it's only number 3, it means that only 3 type of lakes can support this cold water fish. Okay, so this is for the past, this is for the future. Okay, you got an idea. So climate change is not creating a favorable condition for cold water fish. That's we can think about, yeah, because they like colder temperature. Okay, and this is for cool water fish, and so you see that circle, and you see we have large areas red, which is 27. It means for those cities, they can support cool water fish for all the lake types. But in the northern part, it's less, okay, because they have a winter kill for shallow lakes. But when you go to the future, those lakes, the winter kill will be removed, so they become 27. Yeah. But this red zone, okay, has been shifted, okay, and there's some reduced speeds. But for the climate warming, it's very favorable for warm water fish. Okay, so in the past climate condition, only in the northern part we have some lakes for the winter kill. But in the future climate, in the whole U.S., everywhere, all the lakes can support like warm water fish in that way. Okay, so that's given us overall big summary and for the study for contiguous USA. Okay, the last part I'll talk about is the Cisco Lake. And Cisco is called water fish, and you saw this is Minnesota in the north part of the USA. Even in Minnesota, the southern Minnesota lakes cannot support Cisco. Only some central or north of lakes and those very clear lakes can support Cisco. So this fishing habitat is very sensitive to temperature in that way. Okay. So this is to show you in 2006 the weather was warmer. So there's like many lakes had like Cisco kill, and they show you Cisco mortality rate in like late July, early August. Okay, and so we develop our model and we do the like simulation, see whether we can predict that lake at that time. You also have the Cisco kill also. Okay. Okay, we said this study is about the refuge lake. What do we mean the refuge lake? So first of all, you may know the refuge, right? So we want to identify the lakes they can support Cisco in the past and also in the future under climate change. Those lakes is called the refuge lake. Okay, because the state of Minnesota, they got some fund. They want to protect their lakes, but they don't want to invest $1 million to protect the lake. But in the future climate, this lake cannot support that fish at all. Okay? So they asked us to do the project, identify those lakes they can support Cisco in the past and in the future, and then we select those lakes to protect. There will be more value. Otherwise, you select a lake, put a lot of money, invest, protect it. But when the future climate changes, just based on the temperature change, they're no longer able to support it, just waste your money. Okay, so that's why we identify. So actually in Minnesota, only 620 lakes, they have been sampled, find out they have a Cisco. Okay, we want to divide these 620 lakes to the tier 1, tier 2. Okay, based on the level of protection, refuge lake. And tier 3, we call the non-refuge lake. Those are lakes, they most likely cannot support Cisco in the future in that way. Okay, so I think that's also an interesting idea, and especially for our civil engineer dealing with the refuge lakes. Because when we do the hydrologic study, we never thought about it in those ideas. Okay, and we also work with the fish biologists. They used a parameter called D.WRE. What is D.WRE? Essentially, it's the water temperature where DO is equal to 3 milligram per liter. So in this diagram, so you see we have the temperature profile, we have dissolved oxygen profile. So in the first of all, you look at the 3 milligram DO, you find the intersection on the DO profile. Then you find a corresponding temperature. Then it's called a D.WRE. So basically, when the D.WRE is lower, and it's a better condition for Cisco, because Cisco need more oxygen. We put in here as using 3 milligram as a threshold. If where DO is 3 milligram, temperature is lower, it's good. Okay, and so this is like the past and future. So we can find out D.WRE every day. And the fish biologists also suggest, so we pick up a window in the late July or early August, 31 days, we take average. So for that case, each day, and we have some benchmark D.WRE in that way, okay? We also, in this case, instead of doing the study for 10,000 lake again, we expand a little bit. We did like 30 lake types instead of 27, okay? But anyway, because we just want to get a more data point. You see, this is a diagram for this 620 lakes, and this diamond, so basically it's 30 data points for location for our 30 lakes. So we run the model for these 30 lake types, and we got our result for D.WRE. Again, we use the geometry ratio for x-axis, take this as a y-axis. You see all the patterns are similar. We use the weather data for international force for weather north of Minnesota, Duluth in the next lower one, and St. Cloud. Okay, and the fish biologists eventually pick up 2, 11, and 17 D.WRE. Okay, so this is give you some idea. Based on our simulation, we take out there the control line 11 and 17. Then we post our lake. Okay, so for those lake is on the upside of 11 is tier 1. Between 11 and 17 is tier 2. Those like solid diamonds, and D.WRE is more than 17. These are non-refugee lakes. Okay, because you see here this temperature is increased in this way. Okay, so eventually we classify all these 620 lakes into like tier 1, tier 2, tier 3 refugee lakes. Okay, we have 3 regions and add all together. So let's look in this idea. So on the past climate condition, okay, 176 lakes out of 622 is classified as a tier 1, 28%. And then 307, 50% is for tier 2. So these two add together is about 78% the lake can support Cisco. Okay, but when we're dealing with the 2 future climate scenarios, okay, this is reduced from 176 to 78, this is 84. 387 to 127 to 127. So you see these add together about like 34 or 33, okay? So reduced from original 78% to only 34%. So it means that many lakes is no longer able to support Cisco, okay? And okay, this is show you the special distribution in the home Minnesota, and those like open triangles is a tier 1, and then this diamond is a tier 2, and those are non-refugee lakes. Okay, so give you some idea. This I just want to acknowledge, like this fish biologist Peter Jacobson Donna Perrier, and worked with us and helped us. And Hi Stephen is my academic advisor for my graduate study and postdoc. After that, we worked as a colleague many years, and we have good communication. Actually, when I got in here the second day, my wife sent a picture. My advisor sent me a Christmas card. We still have communication. And I started with him in 1990, so that's after 30 years, we still have good friendship. So hope someday these old students will write a Christmas card to them. Yeah. Okay, I think that's my presentation. Thank you for your attention, and any questions?
I have, you don't need the microphone anymore. You switch it to the other microphone.
Okay.
Don't worry. I have a question. I've seen these summer kills. We are more concentrated in Florida, Alabama, in the south part, but not in Texas. That's because the fishes that live there not that strong in Texas, for example. In the west coast.
I don't know. Okay, and this sometimes may be related to particular fish type. Okay, and also maybe related to specific water quality condition in that area. Okay, you see, we do studies of whole contiguous U.S. and climate change. You get general ideas, but when you go to particular water body, so maybe there's some you need to consider all inputs factors to look at that particular fish species. Something like that. Yeah. I know this is something different from your normal civil engineer study, yes. And but I hope you feel it's interesting. It's linked to our lots of information, especially like you may think about a lot of climate change, okay? And we talk about the climate change dealing with the rainfall, runoff, as more civil engineer. But when we're dealing with lake, dealing with the fish habitat, and how we tackle this problem, and just try to show you some idea what we did.
Yes. I have a question.
Yes.
So congratulations for your presentation. Very interesting. I would like to ask you about the 10,000 lakes you have in Minnesota.
Yeah.
Are all these lakes being monitored? So these lakes are being monitored for the.
I don't think they are monitored all the time. Okay, but they do have a database and to have lots of information. Okay.
And the fish. Do you have a campaign for monitoring?
I think in the US,
temperatures in this scenario of climate change, they will not probably. You are assuming that they will not change their behavior.
Sure, that's a good question. That's a good question. And first of all, it's like in the US, when you go fishing, you need to have a license. That's right. And sure, in here we do not consider like how the fish adapt to climate change gradually, and that's one. And also, if some lakes have a channel connected together, whether they can migrate from one another. So we're not consider those parameters at this point. Yeah, those could change.
So in the conclusion, finally, is that the price of salmon will increase in the future. Probably.
yeah, that's right. Okay, yeah, because they have less impact. There's more impact for cold water fish.
Yes.
In that. Yeah, I think I know that raising the salmon is a large production, and because like in China too, they find some ocean area in this particular zone, they have the favorable temperature condition. They raise the salmon there using those large nest tank over there. But this is about fish habitat, but if you have other questions related to dealing with the hydrology, other things, you got my contact information. If you want to contact me, you're welcome. Okay.
Let's thank again Dr. Xing. Any other question?
In Portuguese, maybe.
Se alguém quer fazer a pergunta em português, eu me prontifico a traduzir.
Saber como que ele encontrou a profundidade de todos os flakes.
Mas são naturais.
Quer saber a profundidade?
Isso.
É muito batimetria.
Em todos os...
É, ainda disse que nem todos eles têm, mas não é.
Other question? Checking. Okay, so I would like to thank you, Professor Xing, for sharing this presentation with us. He's going to be with us until next week, Friday. Friday. So any one of you that wants to exchange some ideas in person can meet him in his office. Otherwise, email him and he will be happy to answer the question. Thank you very much. I will thank again your presence, Dr. Xing, and the funding, of course, funding agencies that made this possible. So, thank you. See you in the next presentation next year.
Okay. Thank you for coming again.